Faithfully delivering value, exploring great books worldwide. Hello, this is Sally's Book Talk. Today I'll be sharing insights on the fascinating materials. Human civilization is a story of material evolution from the Old Stone Age and New Stone Age to the Bronze and Iron Ages, up to today's nanomaterials era. Materials as tools for humanity to understand and reshape nature underpin the progress of civilization and technology. How did these materials emerge in human society, and what effects have they had on us? Today, this fascinating book explores materials that change the world and the science stories behind them. The author, Mark Myodonic, is a materials science professor at University College London. As a fellow of the Royal Academy of Engineering, he has unique insights into material science and loves sharing it with everyone. He has hosted BBC documentaries, and this book won the Royal Society Science Book Prize in 2014, plus Amazon's Science Book of the Year and Physics World's Best Popular Science Book. Next, I'll delve into this book through material applications, building materials, everyday items, and future tech. First up, let's discuss building materials, which showcase human civilization. Their evolution has enhanced living spaces and driven urbanization. In this, concrete, steel, and glass play crucial roles. Concrete is among the world's most versatile building materials, appearing everywhere in skyscrapers and road structures. Iconic structures like the Hoover Dam in the US, France's Malo Viaduct, and the UK's Gravelly Hill Interchange are feats of reinforced concrete. Why is concrete used so extensively? It boils down to concrete's properties. It's made from cement, sand, and gravel. Mixing these with water sets off chemical reactions that create intricate microstructures. These microstructures bond strongly, turning into a rigid solid. Plus, as it sets from liquid to solid, it can be shaped, enabling rapid construction of massive buildings. Before concrete, massive structures took decades to build. For example, China's Great Wall and Europe's stone cathedrals, among others. With concrete, the main structure of the 309-meter-tall Shard in London was completed in less than 6 months. In human history, the ancient Romans were the first to use concrete as a building material. In ancient Rome, there was a place called Pozzuoli with volcanic ash similar in composition to modern cement. The ancient Romans could make concrete by mixing volcanic ash, powder, and sand with crushed stones. Roman ruins and archaeological finds show concrete was widely used in construction, like for the dome of Rome's Pantheon. For 2,000 years, this great structure has stood firm and remains the world's largest unreinforced concrete dome. Sadly, after the fall of the Roman Empire, concrete technology vanished. It wasn't until the late 1860s that Joseph Monnier, a French gardener in Paris, discovered steel and concrete have similar expansion coefficients, solving brittle fracture issues and reviving concrete technology. With technological progress, concrete materials have evolved. Now we have self-healing and self-cleaning concrete. Self-healing concrete involves adding bacteria called Bacillus pasteurizii to regular concrete and the starch they love to eat. These bacteria are usually sleeping. When cracks appear in concrete, they wake up upon encountering water. They eat the prepared starch and start fulfilling their role as repairers. They secrete a component called calcite, which bonds with the original concrete to fill cracks. After bacterial treatment, concrete strength can recover by over 90%. Another type, self-cleaning concrete, incorporates titanium dioxide particles, tiny and transparent, almost invisible on the surface. But when titanium dioxide particles absorb UV light, they produce free radicals that decompose dirt, which is washed away by wind or rain. Churches have used this self-cleaning concrete. Concrete must be combined with steel for sufficient toughness. Next, let's discuss another indispensable material in modern construction, steel. Steel isn't pure iron, but iron with added carbon. The carbon ratio determines its properties. High carbon steel is hard but brittle, while low carbon steel is soft yet very tough. Japanese swordsmiths were the first to master this characteristic. They could distinguish between low and high carbon steel through experience. And they used low carbon steel for the blade body and high carbon steel for the cutting edge. This maintained the sword's toughness to prevent breaking while ensuring sharpness, a perfect solution. However, the Japanese method was too complex for mass production. It wasn't until the Industrial Revolution that Henry Bessemer, an English engineer, invented molten steel production, enabling industrial scale manufacturing. Bessemer's method was simple: obtain pure iron first, then add specific carbon ratios. But how to get pure iron? Melt iron into liquid, then blow air through it. Carbon reacts with oxygen to form CO2 gas, removing carbon and leaving pure molten iron. Adding different carbon ratios then yields steel of varying hardness. Bessemer's invention launched the Grand Machine Age. Steel combined with concrete created reinforced concrete, allowing skyscrapers to rise. Beyond steel and concrete, glass is another essential material. Its shimmer in skyscrapers embodies modernity. Glass's main component is silicon dioxide, the same as sand. To be precise, sand melted at high temperatures becomes glass when cooled. That's why deserts often contain glass, formed when lightning strikes sand. King Tutankhamun's mummy decoration included such desert glass, but relying on such rare events couldn't produce glass at scale. It was the ancient Romans who brought glass into everyday homes. They discovered natron, naturally occurring sodium carbonate, could lower the temperature needed for glass making. This reduced glass production difficulty. Thus, they mass-produced glass windows, an invention of theirs. The four Roman glass inventions, European windows were open holes. The word window originally meant wind eye. The ancient Romans soldered transparent glass to windows using lead for weather protection, sparking humanity's architectural glass revolution. Open glass techniques also produced wine goblets. They discovered solid glass becomes moldable when sufficiently heated. Using iron tongs, they shaped cooling glass, even blowing air into red-hot glass to form perfect bubbles, creating delicate, thin-walled goblets. As production techniques advanced, glass varieties multiplied, enhancing daily life and driving technological progress. Heat-resistant glass particularly enabled chemistry to become a systematic science. This glass contains added boron oxide, which minimizes thermal expansion, letting chemists safely heat or cool glassware. Discussing glass breakage leads to tempered glass, and automotive innovation reducing crash injuries from shards. This life-saving glass originated from the 1640s artifact called Prince Rupert's Drop. Formed by dripping molten glass into water, its teardrop shape has a bulbous end that withstands hammer blows. But pressure on its thin tail triggers a chain reaction, shattering it into powder. These fragments might scratch skin but pose little serious danger. Modifying this property created modern tempered glass, with bulletproof glass as its upgrade. Why can bulletproof glass stop bullets? Layered plastic within tempered glass makes it work. Outer glass shatters to absorb energy, while plastic spreads impact. More glass-plastic layers mean greater energy absorption. One layer stops 9mm pistol rounds. 8 withstand AK-47 rifle fire. For humanity, the most useful glass builds modern cities. Flat, thick, transparent, flooding rooms with light and giving architecture a tech edge. Like glass, many materials quietly enhance life. Next, let's dive into the second key topic. First, common materials in daily life. Plastics. They're everywhere. Fast food containers, plastic bags, plastic cups, and more. Actually, plastic is an umbrella term covering rubber, acrylic, and other synthetic materials. The first commercial plastic in history was celluloid. Celluloid's invention had a simple motive: winning a $10,000 prize. In 19th century Europe, billiards was popular, but making durable balls Hard enough for impacts, yet resilient for bouncing, was challenging. Before celluloid, ivory was used, making balls extremely expensive. To solve this, in 1860, an American factory owner offered the prize. John Hyatt, a printer who dabbled in chemistry, took up the challenge. In 1869, he created an ivory substitute using cellulose nitrate, plant extracts, camphor, and ethanol, naming it celluloid. Celluloid mimicked textures like ivory and sandalwood, satisfying the rising middle class's desires. Shaping celluloid into film strips coated with light-sensitive layers created movie foam. This ideal material for shooting and projecting movies propelled the film industry. In the 1880s, as the only plastic, celluloid boomed. Later came nylon, vinyl, and silicone, with silicone transforming lives broadly. Smooth materials like lycra and PVC conquered fashion, replacing silk in women's stockings. Revolutionary in music, vinyl revolutionized how we record and listen to music. Silicone enabled plastic surgeries like breast augmentation and nose jobs. Compared to plastics, glass, and steel, ceramics have a much longer history. Ancient humans fired clay, discovering it hardened stone like perfect for storing grain and water, creating the earliest pottery. Although it could store food, it was very prone to breaking. 2,000 years ago, craftsmen in China's Eastern Han Dynasty discovered kaolin, a white mineral that became perfectly smooth and crack-resistant when fired. This became porcelain, combining strength, lightness, elegance, and smoothness, soon symbolizing wealth and refined taste, becoming China's namesake. Many Europeans tried making ceramics but failed, even after sending spies to China, who couldn't uncover the secret. In the early 18th century, Augustus II of Saxony was obsessed with Chinese porcelain. He once traded 600 soldiers for 127 pieces. To produce porcelain locally, Augustus ordered alchemist Johann Bettger to develop firing methods under threat of execution. Under pressure, Bottager accidentally discovered kaolin, cracking China's millennium-old secret. On January 15th, 1708, he successfully fired true white porcelain. This day marks European porcelain's birth. Since then, Europe's ceramics rose, while paper, equally ancient but more versatile, surrounds us in books, newspapers, toilet paper, and banknotes. In daily life, we see newspapers yellow rapidly under light. Why? Two main reasons. First, inferior paper-making equipment leaves lignin, a wood component, incompletely removed. When exposed to light, lignin reacts with oxygen to form colored compounds that yellow paper. Second, historical use of aluminum sulfate coating for smoothness. Though smoothing paper, aluminum sulfate creates acidity, making fibers react with hydrogen ions, causing yellowing and brittleness. In the 19th-20th centuries, many Western books used this acidic paper. Actually, the most alluring paper form is banknotes, made from pure cotton, not wood cellulose, to prevent counterfeiting. The main component of paper is short cotton fibers. Banknotes made from pure cotton have a unique texture. Besides making them tougher, resistant to soaking or folding, ATMs detect this texture to boost anti-counterfeiting. Additionally, writing on banknotes with an iodine pen can also verify authenticity. When writing on regular paper with an iodine pen, iodine reacts with starch and cellulose to form pigments that turn black. But banknotes don't contain wood cellulose, so they don't change color. Another anti-counterfeiting trick for banknotes is the watermark, a pattern embedded that's only visible under light. Although it's called a watermark, it's not a water stain or ink mark. It slightly alters cotton density to change light transmission, creating a special pattern, greatly improving life quality and driving rapid tech progress. Next, let's discuss the third key topic: high-tech materials leading humanity's future development. First, let's check out the world's lightest solid and best insulator. Aerogel, A new material made from silicon dioxide has a density only 2.75 times that of air, looking like solidified smoke. Since over 80% of aerogel is air, it has excellent thermal insulation properties. 1 inch of aerogel provides insulation equivalent to 20 to 30 pieces of regular glass. For example, even holding a delicate rose near a flame, with aerogel in between, the rose stays unharmed. Silica aerogel is not only the world's best insulator, but also super light, perfect for spacecraft escaping Earth's gravity into space. In 1997, aerogel was first used on the Mars Pathfinder and has since become standard on spacecraft. As thermal insulation material, NASA scientists also use aerogel to capture space particles. On February 7, 1992, the U.S. Stardust spacecraft used a giant tennis racket-like tool coated with aerogel to collect dust from comets, studying star and comet compositions. Now, development of new aerogels is speeding up. For instance, someone developed a material called X-aerogel that can make the world's lightest, warmest blankets, replacing down comforters and sleeping bags. Others have developed conductive carbon aerogels capable of absorbing toxic gases and more. Another future tech material is carbon in its pure form, existing mainly as diamond and graphite. Diamonds are familiar, extremely hard, nearly scratch-proof, maintaining perfect facets indefinitely. The English word diamond comes from ancient Greek, meaning unchangeable or unbreakable. But are diamonds truly unchangeable? Naturally not. Diamonds eventually become graphite, though this change takes billions of years to observe. With human intervention, this timeline shrinks dramatically. In 1772, chemistry pioneer Lavoisier discovered that heating diamond to combustion made it vanish completely, leaving nothing. He then heated diamond in a vacuum, preventing air reactions, and was stunned when it transformed into graphite instead of disappearing. This conclusively proved diamond and graphite share the same elemental composition, carbon. We're actually more familiar with graphite, like in pencil cores for writing. But graphite holds astonishing potential. It's synonymous with future technology. First is lighter, stronger carbon fiber, spinning graphite into threads woven like fabric. Lighter than aluminum, yet stronger than steel, plus corrosion resistant. Best carbon fiber replaced aluminum in aircraft and traditional rackets, vastly improving performance. Graphite can also manifest as graphene. Graphene is graphite's fundamental unit, just 1 atom thick, making it the world's thinnest, toughest, hardest material. It conducts heat faster than any known material and has lower electrical resistance for quicker conduction. This means graphene could become mini power plants, replacing silicon chips as the core of all computing and communication. See the world through the lens of materials. Every ordinary item we take for granted hides a rich story. This book is an ode to material science, serving humanity while reshaping our understanding of the world. Such fascinating materials. That wraps up our discussion of this book. Reading notes are below the audio. See you tomorrow.